You've crunched the data, made all of those PCA and volcano plots, and now you finally have a list of differentially expressed genes. Exciting, right? But there's one small problem. This list is really long. Manually searching for each gene online? Exhausting. Thankfully, there's a tool that can make sense of all this, the Molecular Signatures Database, or MSigDB for short. Not familiar with it yet? Don't worry, this video is here to help. Together, we'll explore how MSigDB can transform that overwhelming gene list into meaningful biological insights. We'll cover key concepts like pathway analysis, p-values, and even tackle the tricky topic of multiple hypothesis testing. By the end, you'll be armed with the knowledge to confidently navigate MSigDB and avoid common pitfalls. Ready to dive in? Let's get started. The Molecular Signatures Database currently contains 34,837 gene sets as of December 2024. But what are gene sets? They are defined by a name and a list of genes that are somehow related to each other. For example, the hallmark apoptosis gene set. Apoptosis means cell death, so genes that are typically active when a cell dies are listed. Generally speaking, a gene set contains up to a couple hundred genes. But how do these gene sets help us with a list of differentially expressed genes? The key is pathway analysis. There are many approaches and softwares of varying complexity. My goal is to give you an intuition on how they work by taking a closer look at the most basic method, overrepresentation analysis. The two ingredients for overrepresentation analysis are a list of differentially expressed genes and gene sets. Now we check whether any of the genes of the gene set also appear in the list of differentially expressed genes. In this example, there is an overlap. Anyways, there are thousands of gene sets on MSigDB. There might be gene sets without any overlap at all between the genes and gene sets and the differentially expressed genes. And there might be gene sets where there's a fair amount of overlap. But how do we know that this overlap is not just by chance? Okay, let's look at this from a mathematical point of view. What we are looking for is the probability of k overlapping genes selected by chance. A situation like this is described by a hypergeometric distribution. This distribution roughly looks like this. On the x-axis we see k, the amount of overlapping genes, and on the y-axis the probability that the amount of overlapping genes is exactly k. As we would expect, it is very unlikely to have almost no or extremely many overlapping genes. Thus, a huge overlap is very unlikely to just happen by chance, and we can assume a biological cause for overrepresentation. For example, if in our list of differentially expressed genes there are many genes that also appear in the cell death gene set, aka huge overlap, we can assume that in our sample, cell death is dysregulated. But can we measure the concrete probability for our overlaps? Yes, we can. Let's set the environment for a formula. We need 4 values for the calculation. The number of genes in the gene set, lowercase n, the number of genes in the differentially expressed genes, uppercase k, the number of overlapping genes, lowercase k, and last but not least, the number of background genes, uppercase n. The number of background genes is important. If we look at this example, the overlap seems pretty much like overrepresentation. But if we look at the same setting, just with other background genes, the whole situation is different. Finally, here's the formula. The probability of k overlapping genes selected by chance is the number of ways to choose k overlapping genes from all differentially expressed genes. Now we look at the not differentially expressed genes. This is multiplied by the number of ways to draw n minus k genes that are in the gene set but not differentially expressed from all genes that are not differentially expressed. And this is finally divided by the ways a set of the size of our gene set can be drawn from a set of the size of our background genes. One small detail before we wrap up overrepresentation analysis. What we're actually interested in is the probability of k or more overlaps. Think of it this way. Imagine everyone's height in your country is measured. What good does it do to know that only 0.001% of people are exactly 1.91 meters tall, just like you? Not much, right? But if they tell you that your height puts you in the top 5%, suddenly it clicks. You know that you're taller than 95% of the population, with only 5% taller than you. In gene language, we want to know how likely it is for the overlap between genes in a gene set and differentially expressed genes to be that big, calculating the probability cumulatively, hence the sigma. What I have been indirectly talking about this whole time is the mystic p-value. Let's quickly unravel this before we can move on to the actual database. Our null hypothesis is that there is no relationship between genes being in a gene set and genes being differentially expressed. Overlap is just by chance. The alternative hypothesis is that there is a relationship, probably due to a biological cause. The p-value gives us the probability of observing our result, or something more extreme, assuming the null hypothesis is true. In our case, it's p of x being greater or equal to k, the likelihood of getting k or more overlaps by chance. When conducting an analysis, we set a significance threshold, like alpha equal 0.05. If the p-value is below this threshold, we reject the null hypothesis. This means we believe that the overlap is unlikely to be random and is instead likely due to a biological cause. While the p-value is a measure of statistical significance, it doesn't tell us anything about the effect size. In other words, a significant p-value doesn't automatically mean the biological effect is large. It simply means it's unlikely to be due to chance. Et voila! Now you understand the p-value and its role in overrepresentation analysis. Okay, now that we covered the basics, where do I find this database? The MSig database can be found at our website gcea-msigdb.org. The database is freely available. Click on Molecular Signatures Database. Each gene set has its own page. Let's take a quick look at it. Click on Browse on the left panel, scroll down, and here you see a linked list to all gene sets. Let's have a look at one. Every gene has a systematic name. Here you can see a short summary and the abstract of the gene set. If you need more information, the source is linked down here. And last but not least are the download links for the gene sets. Pick the format your software requires. Let's get back to Molecular Signatures Database. The most interesting part can be found on the right side, the gene set collection. As you can see, there are human and mouse collections, but in this video I will focus on the human collections. For human gene sets, there are currently 9 collections, which are all of different use. C1 are positional gene sets. The gene sets are named 5p15, for example. This means that all genes of this set are from the 5th chromosome on the short arm, P stands for petite, in region 1 and band 5. These cytogenetic bands can be useful for identifying effects related to chromosomal deletions or amplifications and other regional effects. So if genes of closed gene sets are all up or down regulated, it might be a sign that there is a problem in a specific region of a chromosome. An exemplary condition is the Cri-du-Chat syndrome, where deletion on 5p15 took place. Let's look at another collection. C2 is a rather big collection. This curated collection is divided into 2 subcollections. The first one, CGP, focuses on chemical and genetic perturbations. This data mostly stems from curating biomedical literature. The subcollection specifically aims for the gene sets that were found by perturbation experiments, that is, experiments with non-generic biological and clinical states. For example, in the Ramaswamy metastasis up gene set, genes are found to be upregulated in comparison to primary cancer. The other subcollection is called canonical pathways, CP. It contains pathway gene sets curated from major databases like Reactome, CAG, and Wikipathways. C4 are computational gene sets. It is called computational because its gene sets are derived through advanced data mining and computational analysis of large-scale cancer-related gene expression datasets. Instead of being manually curated or experimentally generated, these gene sets are identified using algorithms and statistical methods that detect patterns, correlations, and modules from vast amounts of gene expression data. When working with this database, it is totally not advised to just use every collection and see what the results are. Why, you might ask? Well, First of all, there will be a lot of redundancy since there are so many sources from which the gene sets are put together. Overrepresentation analysis is based on the concept of a substantial overlap being very unlikely and thus leading to the assumption of a biological cause. However, this concept breaks if we repeat the test for all 35,000 gene sets. If we look at the simulation, if we do our test with more gene sets, it happens more often that an overlap of a high degree occurs by chance, even though it is unlikely by itself. There are multiple ways to correct for this phenomenon, for example to scale the significance threshold with the number of gene sets tested. Another, quite intuitive way to deal with multiple hypothesis testing, however, is to not test the multiple hypotheses. Carefully select the collections that make sense for your experimental design. To put it in a nutshell, when having found differentially expressed genes, go to MSigDB and choose gene sets out of a suitable correction. Set a significance threshold, for example alpha equal 0.05. Calculate the p-value for each gene set. Apply correction for multiple hypothesis testing to calculate the adjusted p-value. If the probability after multiple hypothesis correction meets the significant threshold, the gene set is overrepresented. And that is how we receive a human understandable list of themes out of a very long list of differentially expressed genes. And there you have it! When faced with a daunting list of differentially expressed genes, MSigDB helps us uncover the biological pathways that truly set your groups apart. We've peeled back the layers of overrepresentation analysis, demystified the p-value, and tackled the challenge of multiple hypothesis testing. With these tools in hand, you're ready to take your analysis further and extract meaningful insights from your data. Of course, this is just the beginning. There's so much more to discover in the world of bioinformatics, but for now, you're well equipped to continue your journey. Thanks for watching and happy analyzing.